Welcome back to section 21. In this video we'll be solving for the response of a RLC circuit in series. So most of the time when you see these problems, they're not going to give you a diagram, they're just going to tell you that they're all in series or all in parallel. It's a pretty common thing. If they're not, they'll give you an actual diagram, but most of the time for these problems they're just going to say, hey, they're all in series or hey, they're all in parallel. And that influences how we solve them. So I went ahead and drew the circuit as it's described. So we have a 5 Henry, a 30 ohm, and a 1/125 farad. We were given some initial conditions and we were asked to find I of t for t greater than 0. If you notice that these are all in series, so that means they all share I, which means that I want to go around and use KVL since they all share I. Basically, I want to do a loop. They all share I. If they're all in parallel, then you want to do a KCL because they all share voltage. Okay? That means I want the voltage equation because I'm going to do a KVL. I'm going to say V plus V plus V plus V is what I'm going to do around here. So we'll start with the easy one. We have V equals IR. For an inductor, it's V equals L. Dt. Again, if you don't have these, put them on your equation sheet. And then for the capacitor, I'm going to have to use the integral form. If you don't remember what it is, then you can write out I equals C dV dt, and then invert it. And you'll get V equal to 1/C integral I dt. So I'm going to use all of those because I want to just add up all of my different V's with the same I, so that I have one variable. If I try to do a KCL, I'd get multiple voltages, and I'd have too many variables in my differential equation. Alright, so we're going to do a KVL around I. So I'm going to write this in a way that we're going to use it later as well. But basically, I'm going to have the voltage through the inductor plus the voltage through the resistor plus the voltage through the capacitor all equal to 0. Okay? So this is the voltage through the resistor, the voltage through the inductor, and the voltage through the capacitor. Just to be clear, let's sub those in. Alright, so VL will be 5 di dt. Again, it's I because it's I here. If this was Ix, this would be Ix. This will be I times 30, so we'll just call it 30I. And then we have 1/C, so 1/1/25 is 125, convenient. And then we're going to integrate I dt, all equal to 0. Now I need to get this all in differential, so I only have a first order here, but I have an integral, so I need to make sure all these are derivatives or higher. So you take the derivative of both sides. That means if you have a forcing function over here, you will take the derivative of it in the future, but it's 0, so it doesn't really matter here. So we will get 5 di dt squared, sorry, the second derivative of I, plus 30I, di dt. So I've worked this problem, which is why they're in the right order, but if you don't get in the right order, it's not a big deal. And then plus 125I, all equal to 0, so the derivative of 0 is 0. Then we clean this up by dividing by 5. Again, we want to get a coefficient of 1 up here if we can. It's not that important in this case, it's because I'm not really going to be pulling s immediately out of here, but it's nice just to have it in standard form. So we'll have second derivative of I plus 6 di dt plus 25I equal to 0. So this is our standard form. So this is where we got to example 1. Now, we know the response of this is going to take the form I of t equal to I particular plus I natural. We know that I particular is 0 because the right-hand side is 0. Okay? The natural response, we don't know what the form of it is. We need to find what our s's are, what our roots or our decay rates, whatever you want to call them, what those are. So let's do that next. So we're going to have a s is equal to, so I'm going to have a 6 plus or minus square root of 6 squared, which is 36, minus 4 times 25, which is 100, divided by a 2. So just doing the math real quick. Again, we did that, so that's the 6, and there's 25 times 4. When you solve that, you will get a negative 3 plus or minus a j4. So this is underdamped. We're going to get some oscillation, some sinusoidal action here, which means that our I natural is going to take the form e to the negative 3t. So the negative 3 is here and here. Okay? And then we're going to multiply that by the quantity a1 cosine 4t plus a2 sine 4t. And that 4 comes from here. Okay? So cosine and sine. And if you flip them, it doesn't matter, because we're just going to basically, this constant is tied to the cosine, this constant is tied to the sine. If you flip them, it doesn't really matter. If you put the sine first and the cosine second, it doesn't matter. You'll get the right integration constant later from. Alright, so let's just rewrite our equation. It's just nice to kind of keep an eye up. Where are we? So we have a 0 plus e to the negative 3t a1 cosine 4t plus a2 sine to the 4t. Alright, what should we do now? Well, done. We got the particular response. We have our roots. So the only thing left to find is our constants. So we have 2 of them. But we'll do the easy one first, the one you're thinking of. I have 0 plus. What is that? Well, we're given that. It's 4. So we're going to put a 4 in here. In the future, you will have to find it, but don't worry about that right now. So 4 equal to 0 plus. So that's going to be e to the 0, which is going to be a 1. We're going to get an a1 cosine of 0, which is 1. And then a2 sine of 0, which is 0. So we get that a1 is equal to 4. Convenient. So a lot of times you're not going to actually be able to find your constants right out of the gate. You're actually going to have to get simultaneous equations. So if you get an underdamped or critically damped case, you will find a1 right from the beginning. If you get an overdamped case, you're going to have to do simultaneous equations. It's just how it works. So we got that. So we could rewrite it, but I'm going to save us some space. So now we need to find a2. And you're like, oh, we know v. Okay. Where is v in our equation? It's not in here. So we have to be a little bit creative. So if you remember, I told you I wrote this equation this way for a reason. This is why. So this v of c is going to go back in here. So let's go over here. Alright, we're going to work over here now. Drag this equation over. So I have the voltage across the inductor. Alright, well that is 5 di dt. And I'm going to do all of this at t equal to 0 plus, by the way. So I'll plug in that in a second. The voltage across the resistor is just I times R. Okay. So that is 30 times. So what is the current at 0 plus? Oh, sorry, you can't see what I'm pointing to. Sorry. I times R. I of 0 plus is right here. So I just plug in 4. Okay? And then V of C, you're going to hear like, oh my goodness, that looks horrible. but we don't care. We don't need to use this. This is VFC here, guys. VFC, 200 volts. Just plug in 200 volts. Equal to 0. So the only thing we do not know is di dt. So let's solve for di dt real quick. Di dt will become a negative 64 when you go through the math. Okay, so this is actually di dt at 0 plus. So I have 0 plus, and I now have di dt at 0 plus. You're like, why are you so excited? Well, I have I of t. How do I make I of t into di dt? It's exactly what you think we do. We take the derivative of this, we will get di dt, we set that equal to negative 64. So di dt for our equation down here, so we have an e to the negative 3t, so that's going to become a negative 3 e to the negative 3t, and then our inside will stay the same, so I'm not going to rewrite that. It'll be all of this stuff. And then we will get a plus e to negative 3t, and then we have the derivatives of the insides, which become a, so this is negative 4 sine 4t. Oh, sorry. We already have a 4 here, so there's a 4 in front. So it's 4 sine of 4t. And then I need to pull out a 4 from here. I also need to pull out a negative sign because I went from cosine to sine. So yeah, I'll put the negative sign up here. A whole bunch of stuff happened here. So I took 4 cosine 4t and took its derivative. So the 4 is just from the a1, negative sine, because it was cosine, and then I take derivative of 4t and I get a 4. Alright, go over to cosine. It's an a2. Becomes a over here to sine. It becomes a cosine. No sign changes. 4t, a 4 pops out as well. So there's a whole bunch of mess here. The beautiful thing is, we're going to evaluate this entire thing at t equals 0 plus. So a whole bunch of this stuff's going to go away. So up here, we're going to say that di dt is equal to a negative 3, because our e is going to go there. Inside our quantity, we're going to get just a1, which is a 4. So 4 times 1 plus a2 times 0, because again, cosine sine of 0 is 0. Alright, this becomes a 1. This becomes a 0, because I'm taking sine of 0. This becomes 4a2. So there's a little bit of work here, but if you get the underdamped or overdamped case, it's not as bad. Sorry, the overdamped or critically damped, the derivative is a lot nicer. Okay, so one last step here. Let's get to our final form. We get di dt is equal to negative 12 plus 4a2. So that's the derivative of this function. That's what I have here. Okay. So the derivative of this function is this. This thing comes over here to be this. Now I just smash those two things together. I say, oh, well, and I guess I should say that this is at t equals 0 plus as well. So I'm going to take this negative 64 and sub it in over here. So now I'm just going to say negative 64 is equal to negative 12 plus 4a2. And solve that, you'll find that a2 is negative 13. Put it all back together. bring this thing back down. And write it one last time. I of t is equal to, I'm going to drop the 0 so save space, e to the negative 3t quantity. A1 is 4, so we're going to get a 4 cosine 4t. A2 is a negative 13 minus 13 sine of 4t. And this is 4t greater than 0. And we box it. And I probably say amps as well, but alright. So no lot just happened there. So I just stepped through it real quick at the end. Redrew my circuit based on what it was described. Started off by noting that everything is in series. So I wanted to do a KVL so that I could use the common I, which means I wanted to do voltage, voltage, voltage. So voltage, voltage, voltage. We did our KVL and got our differential equation. Again, you don't have to get the standard form if you don't want to, but it is nice. Once I got the standard form, I used quadratic equation to find my s's. It ended up being a real and an imaginary term, which meant I was underdamped. So I used the equation that we covered in the previous section, the previous videos, and wrote out my equation. Once I got here, all I had left to do was find A1 and A2. I found A1 by just subbing in our I naught. And then I found our A2 by noting that this is a bunch of voltages, so I subbed in a bunch of voltages and currents at t equals 0 plus. So the 200 was for the capacitor. For the resistor, I knew the resistance, I knew that it was 4 amps and 30. And then all I had left was the di dt. I solved for di dt here, and I equate it to the differential equation of this thing, which we took a little bit of work, but we got the differential equation. We then said, okay, negative 64 is equal to the derivative of this thing, solve for A2, and then we're done. All right, so hopefully that helps. If you have any questions, feel free to reach out.